Okay, welcome back. All right, in the last video, I said that when we're doing mass relationships, if they only mention the amount of one of the materials, then we know that that reactant, for instance, would be the limiting reactant, and the other one would be an excess. If they only mention the mass of the product, then it doesn't matter which one is limiting. Okay. What if they mention the mass of both? We said that it's really not practical to go into the lab and try to measure out the exact molar relationships. So it actually, when we get to equilibrium chemistry in the fourth Markov period, we'll see that there's something called Le Chatelier's principle, where there's actually a benefit to making one of the chemicals an excess chemical. But for now, we'll deal with a problem like this. All right, suppose we have 140 grams of chlorine and we're going to react it with 180 grams of sodium iodide, and we want to know how much sodium chloride is produced in this reaction. Okay. In order to do limiting reagent, the first thing you have to do is determine which one is limiting, because it is ultimately the limiting reagent that dictates how much product you get. In other words, once one of the chemicals runs out, the reaction stops. It's just a matter of which one is going to cause the reaction to stop. So what you have to do is you have to take each of them and you have to figure out how many moles of product. Whichever one gives you the least amount of product, that is the one that gives you the actual yield. So actual yield equals least amount product. Okay, so we're going to do this stoichiometry for both of these. We're going to do 140 grams of chlorine, and we're going to figure out how many moles of product we get. So, set up our fraction, convert that to moles, and then from there we can use the balanced equation to go from moles of chlorine to moles of our sodium chloride product. So now I can fill in the numbers. I look up the mass of 2 chlorine atoms on the periodic table. So I get 35.453 times 2, and that's 70.906. And then I look at the balanced equation. According to the equation, for every 1 mole of chlorine, I produce 1 mole of sodium chloride. So how many moles would 140 grams? If 140 grams was limiting, how many moles theoretically would that give us a product? And I get 1.97. So in other words, 2 sig figs, so we get 2.0 moles of sodium chloride. So now we're going to go back and we're going to do the same thing, but we're going to use the sodium iodide. So 180 grams of sodium iodide, set up our fraction, oopsie, and we get grams of sodium iodide, convert it to moles so we can use the balanced equation. And then once we have that, we can go moles of sodium iodide compared to moles of sodium chloride. So I look up the mass of sodium, which is 22.990, and I add it to iodine, which is 126.905. So that's going to be 149.895 total. And then we look at the balanced equation. For every 2 moles of sodium iodide, I get 1 mole of sodium chloride. So 180 divided by 149.895 divided by 2 gives me 0.60 moles. All right. So that means our sodium iodide is our limiting reagent, and our product yield is going to be the 0.6 moles, because that's when the reaction stops. So that 2.0 moles of sodium chloride, who cares about it? It's not going to dictate our final answer. Now they want the mass of the sodium chloride, so now that I know the moles, I can convert that. 0.60 moles of sodium chloride, and let's convert that. Look that up on the periodic table. 1 mole of sodium chloride gives us 22.990 plus 35.453. We get 58.443 grams. And so now we just multiply that by 0.6. So we get 35, our yield is 35 grams of sodium chloride. So again, limiting reagent. How do you know it's a limiting reagent problem? Well, first of all, it was in the title, but it's not going to be on the title on the test. They're saying, hey, use a certain amount of one reactant, use a certain amount of the other reactant. So that means we have to figure out which reactant gives us the least product. And the least amount of product is going to be our yield. So we calculated it for sodium iodide as our limiting reagent, and then we use that to get our final answer. All right, percent yield problems. When we are dealing with chemicals and we're transferring them from container to container, we're going to lose some of our product. So we can calculate a percent yield. How much did we get versus how much should we have gotten? So percent yield is going to be our actual yield. In other words, how much did we collect in the lab, and divide that by the theoretical yield. Now the theoretical yield, I'm going to stop at that point. Theoretical yield means you got to do the stoichiometry in order to figure that out. In this problem you don't, because it's given to you. And we're going to take that answer and we're going to multiply it by 100%. So let's go through the problem. There is our actual yield. The amount of product produced was 45.96 grams. And then we calculated that we should have gotten 52.81 grams. What was our yield? So we're going to substitute in those numbers. Percent yield equals 45.96 grams. I don't know what chemical it is, so I'm not going to put the label. Divided by 52.81 grams, multiplied by 100%. 4.96 divided by, I said 4.96, 45.96 divided by 52.81, and we get times 100, 87.03%. Now that would be great if they told you the theoretical yield, but they're not. They're going to make you work for it. Here's a more realistic problem. All right, we got the combustion of pentane. How much pentane? 36 grams. How much product did we collect? The student collected 104.2 grams of carbon dioxide, which is a product. So we know our actual yield is 104.2 grams. Okay, well, what about our theoretical yield? Well, we're going to have to calculate that. So is this a limiting reagent problem or an excess reagent? All right, they don't mention the oxygen needed for the burning, so that's going to be an excess. But they do mention how much pentane, so that's going to be our limiting reagent. So let's calculate our theoretical yield. Do a little stoichiometry here. Sorry. All right, so start with what they give you. We are actually burning 36.0 grams of pentane. So I'm going to convert that to moles. 1 mole of pentane is 5 times carbon. So we'll do 5 times 12.011 plus 12 times hydrogen, 1.008. And that gives me 72.151 grams. Now, according to the balanced equation, for every 1 mole of pentane, we produce 5 moles of carbon dioxide. And now they want the mass of carbon dioxide, so I'm going to have to convert that. So I look up carbon dioxide on the periodic table. I think it's 44.009, but I'm going to calculate it anyway. 12.011 plus 2 times 15.999. Yep, 44.009. A lot of these reactions produce water, or they produce carbon dioxide. I always tell my AP students, it's probably a good idea to memorize the mass of carbon dioxide in water. You don't have to. You can look it up, but it will save you some time on the test if you have it memorized. So now I just do the math, multiply and divide according to what I set up, and I get 109.7922413. So looking at 3 sig figs. Oh, I'm glad this came up. So this comes out to be 110 grams of carbon dioxide, but putting that little dash over the 0 or putting a decimal point after is not the way that you answer. You answer in scientific notation. So this would be 1.10 for 3 sig figs times 10 to the second grams of carbon dioxide. That's one of those rare times where we have to convert that to scientific notation. Now they're asking for the percent yield. Okay, well now that I got that, I'm not going to repeat the formula here because I wrote it in the last problem. So my actual yield was the 104.2 grams of carbon dioxide that they said was collected in the problem. And then my theoretical, now in the work you can do this old-fashioned thing. I'm okay with it in the work. I'm just not okay with it in the final answer. So 110 grams of carbon dioxide with 3 sig figs. That's what that dash over the 0 means. So we do 104.2 divided by 110, and we get times 100%, 94.7% yield. All right. So now your question is, can you have, well, I don't know if you said but it sounds good. Can you have percent yield and limiting reagent in the same problem? Well, my friends, I'm glad you asked, because yes, you can. Here's a problem. And we're just going to do the second part here. Compute the heat of reaction when 54 grams of chlorine reacts with 98 grams of potassium bromide. All right, so if we collected a certain amount, then we could do a percent yield thing here. So I'm just going to guess, I don't know, let's make something up. Suppose they tell us that we're going to collect, I don't know, let's do, let me see, what do we got here? 3/4, and bromine is about 160, 120. Let's say we collect 109 grams of bromine, actual collection. What is the percent yield in this problem? Okay, so now I can do this as a limiting reagent. How do I know it's a limiting reagent? Again, glad you asked, because they mentioned 54 grams of chlorine and they mentioned 98 grams of potassium bromide, and they don't tell you which is limiting, so we got to determine that first. All right, so let's do a little stoichiometry here. 54 grams of chlorine. Let's convert that to moles. And then let's use the balanced equation. 1 mole of chlorine gives us how much bromine? 1 mole of bromine. Okay, so now we look up the mass of chlorine, and it's 70.906 grams. So we do 54 divided by 70.906. So I get 0.76 moles. That's moles of bromine. Okay, so now I'm going to go back and repeat the process. 98 grams of potassium bromide. I'm going to convert that to moles using the periodic table. And then I'm going to come back and use my balanced equation. According to the balanced equation, 2 moles of potassium bromide will produce 1 mole of bromine. So now I look up the mass of potassium bromide. So potassium is 39.098. And I'm going to add it to bromine, which is 79.904. That gives me a total mass of 119.002. So we do 98 divided by 119.002 divided by 2, and we get 0.41 moles. All right, so that means this 0.76 does not happen. The 0.41 does, and our potassium bromide is considered our limiting reagent. Okay, well, let's see how much bromine we actually get from that. 0.41 moles of bromine, and we're going to convert that to grams. So for every 1 mole of bromine, take the mass of bromine, 79.904, multiply it by 2. I'm going to get a yield over 100%. That's what I get for trying to come up with a problem real quick off of the top of my head. But oopsie poopsie, I'm not going to redo the video. Let's use this as a learning moment. So I get 65.5, so 66. We round to the even number, 66 grams of bromine is my yield. So let's change this original value. Let's say our actual yield was not the impossible 109 grams originally. Let's turn it into a value like, I don't know, something that we really could have gotten, like 61 grams. We'll use that instead. So now that I know my theoretical yield rather, now I can compare it to my actual yield. So I get percent yield is equal to actual yield over my stoichiometry, theoretical yield, times 100%. So my actual yield, I said, was, I changed it from 109 because that was impossible, 61 grams of bromine over 66 grams of bromine times 100%. And we get 61 divided by 66. So we get times 192% yield. So there you go. Those are the two type of problems: limiting reagent and then percent yield. And of course, we could always do a combination of excess reagent with percent yield or limiting reagent with percent yield. But those are the basic constructs. Again, the same technique over and over and over again. Grams to moles. The base unit for this is the mole. Keep converting back to the moles. And then the balanced equation is your mole ratio. So